third day of P'Con conference. And today we have a very exciting talk related to visualization, and especially in-situ visualization. Some of the projects from the PACER project are working on developing some more sophisticated visualization techniques for their codes, where it become so complex to actually store the the results of the simulations or various steps of the simulations to then process them to run some post-processing of that or some visualization afterwards, that we are trying to explore other techniques like in-situ visualizations that are available. And Jean Favre, from who is a senior visualization software engineer at CSCS in Swiss National Supercomputing Centre in Switzerland, has a lot of experience actually in that area, and we were able to invite Jean to present his talk and provide us with some also technical details of how your codes can be integrated with things like ParaView-Catalyst or a couple of other tools that will be Ascent that will be presented today in the talk. So thank you so much, Jean, for joining that early in your time. We really appreciate that, and it's also great to have you back presenting at Pawsey, and the stage is yours.
Thank you very much for the introduction. Okay, I gotta get warmed up, everybody. As I've discussed with the organizers here, it's 5:30 in the morning here, so I'm still a little bit shaky. Okay, nonetheless, I think we have an exciting talk indeed, because I've put a lot of energy in making that happen. So because it's so early in the morning, I thought I might forget some things. So I might as well say thank you right away, so that this is one thing I've done and I've done well. So first of all, of course, thank you to the P'Con organizers. I was at Pawsey Supercomputing Centre a couple or 3 summers ago already for a week-long training with the ParaView software, and I thoroughly enjoyed my collaboration with the people there, so that was very nice. In particular, Ugo Varetto, Chief Technology Officer at Pawsey, and also Yatu Sivaraya, with whom I've entertained some really nice collaboration and discussions about visualization. I will check the chat every now and then. Yes. And please make sure, feel free to interrupt me at any time, because that would also make this discussion more lively. I'm here talking to my screen. As you know, it's always a little bit difficult. And besides the team, the local teams in Australia, there's also, of course, a lot of people, a lot of actors in the visualization and in-situ development teams, which people I need to thank. So I would think about people at Kitware, the company making the VTK and ParaView visualization software, Berkeley Lab, Oregon National Lab, Lawrence Livermore, Los Alamos, Sandia, and many others. There's really quite a lot of people now in this very active development area in HPC. Let me give you just a few words about CSCS, the Swiss National Supercomputing Centre. I work at I've been at CSCS for over 25 years now, where I've always done scientific visualization. I've invested a lot of energy and time really in deploying parallel and interactive visualization solutions to match the computing power available on our supercomputers. And I really insist on the word parallel visualization, because, as you know, with large-scale data, there's really no substitute for parallel processing. And we will discuss that quite at length today. At the moment, Piz Daint runs a large supercomputer called Piz Daint. You can see the picture of Piz Daint, which is a mountain in Switzerland. We name all our supercomputers with the name of big mountains in Switzerland. And we have quite a lot of mountains in Switzerland, so it's easy to find new names every time we replace a supercomputer. Anyway, this supercomputer, Piz Daint, is actually pretty aging now. It has almost 6,000 NVIDIA GPUs, the Pascal P100 GPUs, and then a small partition of a multi-core node. But this will soon be replaced by a new machine coming online in 2023 called the ALPS system infrastructure. And this new supercomputing from the HPE enterprise, of course, will have a strong emphasis on a microservice architecture so that we can give a share of the computer to all our different partners. So I've put here a link if you want to know more about the characteristics of the machine. This is a machine which I believe will be very close in terms of architecture to the machine that is installed or that is being installed currently at Pawsey Supercomputing Centre for you folks in Australia. Now, CSCS provides computing resources and HPC services to a very diverse community. You can see a large chunk of our, here on the left side of my screen, a large chunk of our computing resources are given to chemistry and materials. Then we have physics for almost a quarter of the machine, life science, earth and environment science, mechanics, engineering, and then some other domains filling up the machine. And we serve, of course, a large part of our national community, but also for about 30% of our share, we serve the international community. So this makes it for a very exciting environment where our computing resources range from GPU-enabled computations to multi-core and many-core. And we also have an OpenStack installation offering the standard infrastructure as a service interface. So that's about my presentation here for CSCS. Now let's look a little bit more in what we're going to discuss this morning. I want to talk about in-situ visualization. Why do we need it? Perhaps that's already obvious to most of you. If you are attending this talk, it's because you know that visualization, as done in a traditional manner, is not sufficient anymore to serve the very high scale needs of our simulations. And then we're going to give quite a panorama of the different solutions available today to implement in-situ visualization. I will talk very briefly about a couple of systems from the previous decade. Libsyn, this is a library that was connected to the Visit application. I contributed to the development in Libsyn. This was, I think, 2011. So already a lot of time has passed since then. Catalyst, which is a library connected to the ParaView infrastructure. And we're going to spend quite a bit of time also talking about the new Catalyst. A lot more coming up in this talk. I'll have a few words about SENSEI, but I will refer you to the Supercomputing21 tutorial where really SENSEI was presented a lot of details. Then I will replay some of the presentations material from the most recent Ascent tutorial, which was also part of the SENSEI tutorial at Supercomputing this year. And then I will detail a practical example, which I have done using both ParaView-Catalyst and Ascent And you will see there is a common denominator in those two solutions, which makes it very attractive to set up an in situ evaluation benchmark. Now, in the past, so the past for me is, yes, about 25 years of experience working at a supercomputing center. And although I'm a visualization scientist, I can tell you that I've spent a lot of time doing something else than visualization, which means programming parallel I/O. Okay? Because we've generated an infinite number of files with our different simulations. And I can tell so many stories about the difficulty of interfacing data that was saved on disk with a particular file format and to read this data in a very efficient manner in parallel with domain decomposition, with ghost cells, all those different details which are necessary to do the proper I/O in order to be able to run parallel visualization. So the most important summary or the moral of the story of the past is really that without I/O, I couldn't do any decent visualization. Okay, so willing or unwilling, I've become not really an expert in I/O. Nothing like, for example, the speakers from yesterday in your P'Con conference about ADIOS. I believe you've had some two excellent speakers who are really experts in parallel I/O. However, I've gained enough experience, or let's say the minimum experience in parallel I/O with MPI-I/O, parallel HDF5, parallel NetCDF, ADIOS, to be able to, again, read my data in parallel to do visualization. And finally, I would also argue that to produce an award-winning animation visualization, I had to repeat many times the load, execute, render cycle that is typical of visualization. So really, the true cost of doing I/O in a simulation campaign is really an aggregate of the solver's I/O phase and the many iterations of visualization sessions. I will show you, for example, in a little bit later this morning, a video which I did for the GTC 2021 conference this spring. And I swear to God, I must have done at least 20 different visualization runs to accomplish that video, which means I have to do 20 times the I/O. Which also means that when we're going to do this in situ, we better know very well what we want to do, because running a high-scale simulation with an embedded in situ visualization scenario is going to be very critical in terms of the consumption of computing resources. But more on that later. So in this era of post-hoc visualization, really saving data to disk and then reading it back into a visualization system, we've always been confronted with the dilemma of either storing as much data as possible, but then slowing down the computation to sometimes some unbearable numbers, or else do save less data. But if we were capable of saving really almost all of the data of our simulation, sometimes it also means that we would need a very high data transfer rate between our simulation machine and the storage system, and we would need a visualization machine almost as big as the supercomputer. In fact, at CSCS, when we put online the Crash supercomputer Piz Daint, since the supercomputer was equipped with about 6,000 GPU nodes, we decided that the supercomputer itself would be the de facto visualization cluster. So I've always joked that my visualization cluster was a 6,000 GPU node supercomputer. Well, besides the joke, it really means that we have an expensive machine that is now the hostage of a visualization deployment solution. So that's not perhaps sometimes something that is always desirable. All right. Now, the alternative is to use smaller data, which we resample, we subsample both in the temporal and the spatial subset. Of course, the big drawback of subsampling, as you know already, is that we run the risk of missing a particular event, a transient phenomena, or a particular threshold. And in any case, subsampling defeats the original purpose of doing simulation at very high resolution. So it's really, this dilemma is really what drives the whole motivations and thinking about in situ visualization. Now, in fact, in situ visualization, that's in contrast. With in situ visualization, we try to enable visualization analysis while the data is being generated or acquired. I know that in Australia, you also have the SKA activity, which is going to bring to the computing center an avalanche of data, bits and bytes. And this is not here data that is simulated, that is data that is acquired from a set of sensors, a set of machinery. And this also has to be treated in near real time. So the concept of in situ visualization applies both to simulation or experiments. Now, when we do visualization calculations while the data is generated, we can, and we would call this co-processing for the moment. We can render images, we can derive images, we can extract features, and hopefully some of those features, at least in the many scientific fields that I'm familiar with, when we extract a feature, for example, an isosurface, for example, a vortex core, etc., this data is much smaller than the original data, the original raw data. So, in fact, in situ pre-processing has the advantage of reducing the volume of data that needs to be stored on disk. Now, we've raised already quite a lot of questions in the last 20 years concerning, the last, well, 10 years, let's say, concerning the use of in situ visualization. The first one is about sharing physical resources and domain decomposition. As you know now, with the different architectures coming up on the HPC scene, we have a lot of different accelerators, accelerator devices, for example, the GPUs and the CUDA libraries. We have different languages which exhibit a very high level of parallelism in terms of not only thousands, but also millions of tasks. And if the domain decomposition is in that range, we need to ask ourselves if the visualization algorithms scale as well as the simulation algorithm. And that's perhaps not always the case. Then the other question to ask is what percentage of time can we afford to do visualization versus move our solver in the right direction. So if we are doing time sharing of a machine, perhaps we cannot afford to spend so many cycles to do visualization. So can we use domain knowledge whenever possible to reduce computations by processing only a subset of features, for example, for the purpose of visualization? And then also, which visualization algorithms, feature extractions fit better on this in this on-the-fly processing scenario? You know that some algorithms, we're going to see that again in the video I will show later on. Some algorithms in visualizations require some pretty fine tuning of parameters. For example, the volume rendering of scalar field, which is a very intensive rendering application, requires very fine tuning of color and opacity transfer functions. So how do we do this when we run on the fly? We'll try to get some answer to that question later on. How about time-dependent particle tracing? If we're doing in-situ visualization, the state of a simulation is given for one time step, or at best, perhaps the time step before, so that such that some averaging can take place. But if we do visualization, if we run visualization algorithms such as a particle tracing, we need access to many more time steps at the time of the execution of the algorithm. So that might not be suitable for an in-situ scenario. If the idea of doing in-situ visualization is about creating some smaller artifacts that we can save to disk because they are smaller, perhaps we actually need to augment this data with some ancillary data, such that we keep with the data the context in which that data was calculated. So that's also an important aspect about reducing the data live and then storing it to disk. And then finally, as we discuss this activity, of course, we are attracted to solutions that would provide a generic abstraction describing data and meshes such that we could reuse our in-situ environment, our in-situ libraries on multiple domain simulations. So I've implied in the previous two slides that we could either do ad hoc post-processing or visualizations tightly integrated with solver. But that's not actually the case. We have many more flavors of in-situ visualization. And in this figure taken from this 2019 paper, we also show the concept, the paradigm of doing in-situ processing in a loosely coupled fashion, also called in-transit. In transit, we replace the I/O phase of the simulation by a transfer phase, which would, of course, use some hardware devices which are faster, which have a bigger bandwidth than the disk system, to transfer data from the simulation to a second set of computing nodes. Being the fact that we use a high velocity transfer subsystem, be it an RDMA setup or others, and probably you've seen that during the talk yesterday about ADIOS, you've seen Scott Klasky and his partner discuss some of the alternatives to do this data staging. So if we are able to do this, then the visualization activity, as we see over here, that visualization task has a lot more time available between each phase of transfer to do its job. However, the issue comes when the next transfer of data happens, which would take place right over here in my image. If the visualization activity, the visualization algorithm that was being executed has not finished, we have the issue about interrupting processing or losing our data. So here again, we have a balancing act to manage between how much data we need to transfer, how often we need to transfer data from the simulation to the second set of computing device. And that's all in the tuning of the environment. We also have to consider here that we have to do two allocations. One allocation for the compute nodes required by the simulation, and a second allocation for the visualization nodes. In place, I've talked about sharing a processor's memory space without touching the disk. Okay, I think we're clear on that. We don't want to do I/O to the disks because that's really the bottleneck of high-scale computing. But if simulation data is moved to this distinct set of resources, as we've seen in the in-transit scenario, we're still analyzing data in place, but is it in situ? So I've already used quite a bit of different terms: in situ, post-hoc, loosely coupled, in transit, concurrent processing. There's quite a few variants on the terminology. And a couple of years ago, it was felt that we needed some proper definitions. So Professor Hank Childs at the University of Oregon led an effort by over 50 different visualization expert practitioners in the world to analyze a bit the in situ scene and give reference to set up the proper terminology for the different in situ systems. So this is the paper that you can download at this particular address here. And for the scope of this paper, in situ processing was defined to be processing data as it is generated. Okay, so it's a little bit of a loose definition, but what we mean by this is that this is no more the post-hoc visualization scenario where we can do visualization without time constraint. Here in situ processing, we process data while it's hot, so to speak. Okay. So the paper made an attempt to describe in situ system via multiple different axes. The first one was integration type. How do visualizations and analysis code, or how are visualization analysis code integrated with the simulation code? The second axis was the proximity. How close is the visualization code from the data? So how do we get to the bits and bytes? The third axis was access. How does the simulation give access to the data? So there are issues about permissions and so forth. Division of executions relate to how compute resources are shared between simulations and in situ routine. Operation controls is about the mechanism for selecting which visualizations operations are executed during the runtime. And then finally, we have the output type, which defines properly which types of operations are performed on the simulation before it is output. So to give a few more details about those different axes. In the integration type, we've made the difference between the application aware and the application unaware systems. In an application aware category, we have, of course, the traditional, or I would say the early implementations of in-situ visualizations, which are the bespoke implementations. Here we have a dedicated simulation and some dedicated code that is embedded directly into the simulation. Of course, it can access the data in the most efficient way because it's extremely tied to the simulation code. But the difficulty here is that in most cases, this is code that cannot be reused with a different simulation domain. Then we have the systems based on a dedicated API. Of course, the data needs to be marshaled to the visualization subsystem via an API. We have dedicated APIs such that systems like Catalyst and Libsyn, they are dedicated in the fact that the history is such that at the beginning there were visualization applications such as ParaView, or Visit. So the interface or the API for this visualizations application was strictly related to visualization. So of course, the link to an in-situ use of those libraries is, I would say, limited to visualization. Then we also have the multipurpose API, and Adios is an example of that, for example, where in addition to visualization and analysis operations, we can also do we have some additional hooks to do data movement and different I/O, different data filtering, compression, etc. operations. In the application unaware subcategory, we have, for example, the interposition implementations. With interposition, we mean the use of a library interface for something other than its original intent. If you think about dynamically loaded libraries, which are replaced by a substitute, this would be an example of interposition. So if I'm calling, for example, an NPI-IO library, if I'm making an NPI-IO library call, I believe it's doing IO, but if I've replaced underneath that library by a library doing something else, for example, visualization, then transparently, my code, my data is being moved to an in-situ visualization library. So this would be interposition. And then inspection, in the inspection last item, this would relate to our debuggers or profilers inspect the memory space of a given simulation in real time to draw some conclusions about the data. In my second axis, in the second axis, we've looked at proximity, which is really about the cost of accessing data. That cost can be expressed in time or also in energy. I think, since the top 500 category, there's also the green 500. So energy is also something that we need to be aware of. And as we move data across memory hierarchies, as you know, it costs not only time, but also energy. So we have here the distinctions between on the node access, of the node, but on the same computing resources, or else on a distinct computing resources. And this would be the case of the in-transit processing that we've talked about earlier. This would be, of course, at the very end of the spectrum. This in-transit, also called data streaming by some people, would be is really stretching the issue of doing in-situ visualization. Access data is about looking at the same logical memory space is shared by simulation and visualization routines. Of course, our first reaction would be to say we want to do shallow copies everywhere, because shallow copies doesn't cost any memory. We can have the simulation data and the simulation code and the visualizations code look at the same memory space. However, the alternative, which is deep copy, could also have some advantages. Think about the cases, for example, where we have a different memory layout. Think about the distinction between structure of arrays or arrays of structures. In that case, we really do need a deep copy of the data space from the simulation to the visualization code. Another use of doing a deep copy would be if we cannot afford to slow down the computer so much, to slow down the simulation so much, and we'd like the simulation to continue while a subset of computing resources, for example, do the visualization. In that case, with a deep copy, we are able to run two concurrent activities on the simulation data. So this is something to keep in mind. Let me check the chat here for a second. Yeah, so there's the first question I see here on the chat is, would snapshots of images at every time step be defined as in-situ visualization? Yes, of course. I think the primary use of visualization in general is, in any case, to render some images. So we will talk about this in the final category I have here on the axis describing the in-situ system. But let me go back to our fourth category, which is division of execution. We can have a space division where we have disjoint computing resources. It can be a subset of the computing resources already allocated, or it can be a set of compute resources allocated from a second allocation. Or we can have the time subdivision for execution, where we alternate between giving the computing cycles to the simulation or to the visualization. Then comes the operations control. This is about selecting which visualization operations we want to execute as part of our analysis. In automatic control, we would have both the adaptive or non-adaptive categories. In a non-adaptive scenario, we would have a fixed visualization pipeline. When I talk about visualization pipeline, it's usually, it's a common definition where we have a data source, a data producer, and then we have a different set of filters which take place one after the other, and that's called the pipeline. And then the end result is either an object that we can save to disk, a three-dimensional object, or the output can also be an image. But this is all, for every time step, we have a fixed pipeline. Or in the adaptive case, this is about being able to choose different paths of executions, perhaps based on a set of of user-defined parameters or on a set of triggers, on a set of queries. If at a given time step something is happening, I want to do a different execution of my visualization algorithm. So this would be adaptive, but still it would be scripted in the sense that it's automatic. And then we have human in the loop. Human in the loop would be, of course, of great interest to monitor the state of an ongoing simulation, to test the quality of data, and eventually to enable computational steering. So this is, of course, very important. And here we have two different possibilities. One of them is blocking, interrupting the simulation to inspect the data, or we have a non-blocking category to implement this human interaction. Now, since I've talked about doing human in the loop, I could ask the question, so what about feature extraction? What is a feature? Of course, for each of you, you have different simulations domain. A feature would be something different. In the case of fluid dynamics here, in this simulation of the aerodynamics of an airplane, a feature of interest in that case was this particular vortex core at the tip of the wing. Now, of course, I've taken this picture from my archive of showcases in visualization. This is not a feature that was extracted in an automatic fashion. Although perhaps today there are some sophisticated vortex core extraction filters which can find that vortex in an automated fashion. However, at the time of the creation of this image, I actually had to fiddle quite a bit in an interactive manner with the data to find the proper positioning of my streamline extraction filter to define this particular vortex. So really a feature will be depending on which is your domain of application, and will be depending on domain knowledge by the experts. So there also comes the issue between having a generic in situ visualizations coupling and being able to use some of your personal experience, your domain knowledge to drive the feature extraction. So this is why having a way of adapting the computation is, of course, of great interest. Without interactive data exploration, it's really, really difficult to do visualizations. And also something else to consider is that, for example, in the case here of this vortex extraction calculation, I have here an expensive calculation. So if I can avoid doing it when I know that the flow is in a quiet state, then so much, then I'm in a better situation. When I know that a vortex core can happen, at this time, I need to trigger the execution of this vortex core extraction. So that comes the motivation for doing interactive or adaptive, I should say, data exploration. The final output type that was considered in our discussion was the shape, if you want, or the manner in which we save data. So in the subset category, we would have the resampling, the region of interest selections, the query-driven subsampling. In the transform, we would have the way data is usually manipulated in the visualization algorithms, and then the derived nature of an output was thought to be either fixed, for example, a snapshot, which has a fixed resolution. So this is something that we can more or less tune in terms of the need we have for I/O resources, or we can have proportional output. If you're doing computation of an isosurface along a time-dependent simulation, of course, that isosurface of a particular scalar field will have different sizes as time goes, and we cannot predict, and that's the point, we cannot predict how much I/O will be necessary to output the data to disk. So in summary, the outcome of this paper, about 15 existing systems were reviewed, and half of them, perhaps that doesn't come as a surprise, implement a time division with on-the-node proximity, which means that the simulation advances, pauses, gives control to the in-situ library, and then the control goes back to the simulation, and we do this in an iterative fashion. So for example, we have Ascent, which I will present in quite a bit of details later on. We have ParaView-Catalyst, we have visit Lipsin. Other examples include Adios, SENSEI, which can also operate on different modes, sending their data to distinct resources. I'm sure the folks from the Adios team yesterday covered that in quite a lot of details. So just for reference, I've added here some of the features that Adios allow you to do in terms of data storage, data staging, data compression, filtering, and coupling. And I'm actually looking forward to see the presentation that was done yesterday during some later time this week. So I will review the recording of that. SENSEI is a system of great interest, actually. We've talked about the ability to have a coupling that is generic, and this is exactly what SENSEI provides. It's a generic API where you write the data adapter once, and you can reuse that data adapter with multiple environments. So with a set of parameters which are configured at runtime, using a SENSEI enabled simulation will give us access to different backends, for example, Adios, Lipsin, Ascent, Catalyst, and also some dedicated Python code. So this is a very, actually very interesting system, which I encourage you to look at if you are looking for the possibility to address multiple backends for your in-situ visualization needs. For more details, because there's a very extensive tutorial that was created for Supercomputing 2021, I would refer you to the tutorial notes, which are online on the SENSEI website. So we've talked about data adapters and this ability to write a data interface which can be reused with multiple backends. But in fact, is it easy to write this data adapter code? I mean, do the standard visualization application support the data structures that I use in my simulations code? If the answer is yes, then okay, we have the so-called data adapters. If, however, we have alternate data representations, we need to do data conversion. And there comes the big issue about consuming memory and consuming cycles to interface data between your simulation code and your visualization code. Let me give you an example. Oh, and before I go to that example, I'll also mention the fact that in recent years, we've gone away from the traditional monolithic simulation in the sense that we now run coupled codes, we run ensembles, we use machine learning. So the data structures, the data objects are a lot more than the traditional mesh of grid points. So this is to keep in mind. Here's the example I wanted to present. I've used the NEC 5000 solvers from Oregon National Lab for aerochemistry, combustion, and fluid dynamics problems. NEC 5000 uses spectral elements and nth order polynomial. So in this snapshot of the visualization here, this is a 2D snapshot. Actually, it's a 2D simulation. I've shown in purple on the image one of the spectral elements. And this is an 8th order spectral element, which means that the data was converted to an 8x8 subgrid of points to be able to feed that data to the VTK environment for visualizations. So for GTC this year, we had a 3D simulation, and to better represent the data, we have chosen to use the NVIDIA index to do volume rendering. NVIDIA index is really the state-of-the-art, especially when it comes to unstructured data, a state-of-the-art volume renderer, and that is available today. However, I've done the visualization in a post-hoc scenario, meaning all the data was saved to disk because I was forced to convert the spectral elements to a tetrahedral mesh. And I could not afford to do this in memory. So you have a link to the 3D movie over here on your slide. I welcome you to look at that link. I will actually show you the visualization, the movie itself in a minute. But let's look at the numbers. Here's a snapshot of the 3D visualization. And here's one of those spectral elements here in purple at the bottom right of my screen. One of those spectral elements, which is divided in an 8x8x8 subgrid of points. So if we look at my high resolution data, which had just over 500,000 spectral elements with 12th order, the data explosion is such that that data was converted to 4.5 billion tetrahedra. So this is a fact that precluded us from using an in-situ visualization setup because we could not afford that data explosion. Now, this conversion from higher order elements to linear elements is not limited to NEC 5000 or to ParaView. in the system that I will describe later on this morning, Ascent, when Ascent is coupled with the MFEM library, those high order elements are also discretized and down converted to the linear elements. So we have, again, to pay the price of that conversion. So let's look anyway at the video, because I want to highlight a couple of things. So the video is this. There we go. We have here a cold jet that is injected into a cylinder. And here I'm showing only the very first part of the injection. And I'm going to pause if I can get to it, pause the simulation here and talk a little bit about this volume rendering. At the bottom of my screen here, you see the color table that was used. What you do not see is actually the transfer function that is used for opacity. The process of doing volume rendering is to make data more or less transparent based on different factors. So we can use a given scalar field. We can use the gradient of a scalar field also to be able to remove regions of space which have where continuity is greater. And this is the whole process of doing volume rendering. But it's an activity that is extremely intensive in terms of tuning, because it takes very little to change from something that looks like a big blob of cloudy data without much forms, to something that is like in this picture, that highlights really the different flow characteristics. So this is the visualizations that I had to redo about 20 times, because the difficulty in doing a visualization with a time-dependent solution, as you probably know, is that even if a particular set of parameters looks good at a given time step, perhaps 100 time steps later, it doesn't look good anymore. So the tuning of a visualization algorithm, such as volume rendering, sometimes has to be done over the complete temporal sequence of the data. So that makes it very challenging for an in-situ visualization setup. So do not forget that particular aspect as you plan your in-situ visualization. Okay, let's go back to my discussion here. So spectral elements are one type. Some people call them those exotic elements, but the good news is that more support is coming to us. There's, for example, an issue that was opened recently in the ParaView discussion list about adding discontinuous the lurking finite element mesh support natively into the VTK ParaView setup, which means that those down conversions to linear elements, for example, would not be necessary anymore. And at that time, I can probably afford to do my visualization in situ.